Welcome back to CST432, Microprocessors and Embedded Systems. Today, we are covering Moving On. We have come a long way since the beginning of this course. In this module, we'll provide the big picture of what all this is about. So some of the key concepts that we'll cover here include real-time operating systems, hard versus soft real-time, as well as real-time software architecture. Some questions to keep in mind as we go through this is, how do we ensure that a real-time system is responsive? And secondly, what are the factors affecting an embedded system's design? A real-time operating system is basically like any other operating system in that it provides standardized APIs for accessing hardware features. And in addition, it will manage user tasks running on the system. And of course, there's the trade-off consistency in software development versus memory and resource management overheads. So what's the difference between a real-time operating system and a normal operating system is in how it deals with inputs and events. There are various real-time operating systems available for the NXT. Some examples of open source RTOS include the NXT Mode, NXT OSEK, as well as NXOS ARM debug used in this course. NXT Mode is basically an operating system based on TinyOS. It uses a custom C-like programming language called NESC for developing programs or applications that run on TinyOS. In addition, it emphasizes inter-node communications primitives and is therefore geared towards wireless sensors and other mesh network configurations. On the other hand, NXT OSEK is based on the TOPPER's ATK or Automotive Kernel Compliant Embedded RTOS environment. It uses the LEGO hardware drivers as the basis for its support for the various NXT devices and peripherals. Programming environment is in either C or C++ and is used to develop various real-time systems running on the NXT. We've been looking at NXOS ARM debug, so this should be familiar to you. It is a C-based operating system for the NXT, and it has a streamlined native operating system with a cleaner API so that you can program in both ARM assembly as well as C language. So what makes an operating system a real-time operating system? Some of the real-time system concepts will be covered here, but not in detail. Right. Various strategies have been developed for designing and specification of real-time systems throughout the history. First, for example, there is a modified system analysis and design or SAD technique used to specify time event constraints for real-time systems. Then there are enhanced object-oriented approaches for designing more advanced and modern operating systems using real-time constructs. Finally, there's also an alternative approach called a time-triggered embedded systems development method, which is used to specify real-time operating systems. Now, real-time systems design must address the following three things. First is the response time to events. Secondly, are deadlines in terms of how long the system takes to respond to these events. And finally, how it deals with instantaneous as well as periodic events that comes into the system. First, we look at the response time. It is calculated from the time the input is received to the time that the output is generated, meaning that when we receive an event in our embedded system, it must respond within a certain time, and the time it takes to be able to generate the required output is called the response time. Of course, we are all familiar with deadlines in our daily lives. Now, a deadline in terms of a real-time embedded system is the maximum allowed response time that is specified for an input event. So if deadlines are not followed, the system will be late servicing the inputs. There's two examples here given in the diagram. One is in blue showing the on-time output event response versus the one in red showing a late output event response. So it has missed the deadline. Finally, we need to understand the type of events the system deals with. There are two types. First is called instantaneous, second is called periodic. Instantaneous events occur asynchronously, meaning that it can occur at any given time, whereas periodic events occur at fixed intervals, and it is pretty much predefined for the system. So the sustained load is the system's total periodic event processing time, meaning that it will be busy for a given fraction of the time due to these periodic events. peak load is the system total periodic load and instantaneous event load processing time, and added together, this indicates how much processing overhead is being performed by the operating system and the CPU. So we can define the types of real-time system based on the way they deal with deadlines. A soft real-time system will be able to process most inputs before their deadlines, whereas in a hard real-time system, all inputs must be processed before the deadlines, meaning that they cannot afford to miss any deadlines. Typically, hard real-time systems are used in safety and other critical infrastructure systems. When we talk about real-time system design, in general we must consider the following. First of all, how do we deal with input and output processing? Because that's what the system is used in, the environment, and it has to react to it. Secondly, how does it deal with task scheduling? And finally, what type of processor or controller is suitable for addressing the task at hand? We have studied input and output processing previously, but to recap, there are two types of input and output approaches. First is polling, and second is interrupt driven. Now, polling is not encouraged for I/O because it uses significant CPU overheads. And since I/O events often occur asynchronously, it is difficult to be able to have a consistent response time when we are polling, because the event may occur after we finish the polling step and move on to other processing steps. So interrupts are normally used, and interrupts typically will be done in two stages. First, the interrupt will signal the start of an I/O task, and secondly, another task or kernel level task will handle the processing of the data that is due to the I/O event. Next, we look at task scheduling. One of the issues with real-time systems is that we want to have a consistent and deterministic response time to events. So preemptive scheduling is actually not very suitable for real-time systems because a critical task may be suspended prematurely by the scheduler. And secondly, it is difficult to guarantee a certain deadline will be met because the task may be suspended and will not be resumed on the processor until after the deadline has expired. So in order to avoid this problem, a non-preemptive scheduler would be used instead, because the response time of this non-preemptive scheduler can be controlled. And in reality, hard real-time systems often use static schedulers, meaning that the events that it will process is well known in advance of the actual operation of the system. This avoids having to deal with unexpected inputs and unexpected events. So task prioritization is important. Firstly, I/O tasks obviously have to have a higher priority than user tasks because we want to deal with input events as they occur. And second, this tends to be the opposite requirement for interactive systems, which need to have a higher priority for user tasks in order to provide a good response time to the user generated events and inputs. Next, we look at the choice of controllers. Now, we have studied in the very beginning of this course some of the available microcontrollers in the market, and there are many. So how do you decide which is a suitable controller for use in a given embedded system? The first consideration actually is the unit cost. The reason being that many embedded systems are sold in the millions, and a 1 cent difference between the cost of one controller to another controller would mean a difference in manufacturing cost of millions of dollars. So to avoid this problem, the choice of a controller tends to be dictated by economics first before any other consideration is made. The second issue, of course, is the power consumption. If the system is an embedded system, a portable device that is carried around and runs on batteries, then the lower power consumption of the part, the more useful and effective it is for a given embedded system. Thirdly, the robustness, whether it be used in an outdoor environment, in extreme environments that may even require a mil-spec device. And finally, what is the processing capability of the controller? Is it able to handle the events that is needed to be handled on a normal operation? Processor utilization ratio indicates to the developer how much of the CPU is busy. If it is 0%, the processor is not being utilized and is basically idle. If it is 100%, the processor is fully utilized, or else actually the processing power is insufficient because there may be tasks that are delayed, but because the CPU is 100% utilized, it is not able to execute them in time. The calculation of the PUR value is given by the following formula. It's given by the processor utilization time divided by the available processor time, or else we can rewrite it as the available processor time minus the processor idle time divided by the available processor time. The reason to do this is because the idle time is often measured by a special lowest priority task that is run whenever the CPU scheduler is not busy. This allows us to give an idea of how much of the CPU is actually not being used for normal processing. So with these various considerations, we can define a 3-tier real-time system software architecture. In this diagram, we see the 3 different tiers. The lowest level is the interrupt handlers. Then comes the computational tasks, and of course finally the user interface, which runs on top of it. Now the priority of these layers are different. The highest priority belongs to the interrupt handler level, whereas the lowest priority belongs to the user interface level. Why is it? Interrupt handlers have the highest priority because of the real-time requirement of being able to meet the deadlines within a given duration. So each interrupt handler must have minimal processing inside the handler, because as the interrupt is active, other interrupts will be disabled and will not be processed. So this will increase the system latency and the response time if an interrupt handler takes up too much processing time. So on the other hand, the average processor utilization ratio must meet all periodic events requirements, meaning that any system periodic event has to be able to be processed within the available CPU cycles. However, the peak PUR should meet all periodic and instantaneous events requirements, and depending on whether it's a soft real-time system or a hard real-time system, the peak PUR can hit 100% for soft real-time, but it must be less than the 100% for the hard real-time system. This is to ensure that the hard real-time system is able to guarantee a response time that will meet all deadlines. Next, we come to the computational tasks layer. Basically, these are the libraries that is provided for various processing tasks in the system. The bulk of processing requirement of the system will be handled in this layer, and typically they need to complete the processing within an interval that is between the consecutive periodic events. One example of this is a video frame compression to be done in a video camera must be completed before the next video frame is received. If it takes longer to compress a given video frame than before the next frame arrives, then we may end up having corrupted video output or else lost video frames. Finally, we come to the user interface layer. These deal with asynchronous instantaneous events, and it is actually considered rare to have user interface events for the processor because the speed of the processor is much higher than the frequency of the user inputs. So it tends to be the lowest priority task to be executed at specific intervals by the scheduler. The reason is because most human response time will not be able to detect a response time of 100 to 250 milliseconds from the initiation of a user input event to the actual output from the system. So this response time of 100 to 250 milliseconds is acceptable. All the embedded systems in the world today, we see an emergence of a new platform for developing in embedded systems, which is Linux. Versions of real-time Linux has been developed over the years, and many of them are applied in various embedded systems for soft and hard real-time purposes. An example of a Linux kernel being used in an embedded system is the Android operating system, which is found in many smartphones today. Another Linux operating system, UC Linux, is a small footprint Linux kernel for embedded systems, but it needs a minimum RAM requirement of 2 megabytes, and this exceeds the current next microcontroller resources because it only comes with 64K of RAM. So unfortunately, we are not able to run Linux on the next platform. However, LEGO has just announced the availability of a new platform called the LEGO MINDSTORM EV3 platform. This next generation MINDSTORM is based on the ARM9 processor, which has a 64 MB of RAM and 16 MB of flash, which is enough for running a full Linux kernel and other software on top of it. So it is going to be a Linux-based robotic platform and is coming at the end of 2013. So we shall look forward to more exciting use of embedded systems in the future. With that, we have come to the end of this course. I hope there's been an exciting journey for you, and even as we move ahead into newer platforms and newer environments, that this will be the foundation for you to understand how to develop and how to understand the function of such systems. So an additional question that you would like to look into is, what are some examples of commonly used embedded systems platform, whether it is hardware or software today? Hope you have a pleasant learning experience in the future. Thank you.